Have you ever looked at one of those massive, powerful industrial machines and wondered, how in the world do we tell it exactly where to cut or drill or move with, microscopic precision? Well, it's not magic, it's actually a language. And today, we're going to learn the alphabet of that language.
And really, this is the most important question. I mean, can you imagine the chaos if a programmer in one country and a machinist in another were basically speaking different dialects? Parts would get ruined, machines could be damaged. It'd be a mess. We absolutely need a universal standard, kind of like a Rosetta Stone for machines, to make sure everyone and every machine is on the same page.
So here's our game plan for this explainer. We're going to start with the standard that makes it all work, then learn a simple physical trick to decode any machine. After that, we'll apply it to the most common equipment you'll see. And then, we'll level up to the mind-bending world of multi-axis machines, and we'll finish it all off with a cheat sheet you can use anywhere. Okay, first things first, we've got to establish the ground rules. And this isn't just, some casual agreement between folks. No. This is a formalized international standard that really keeps the entire industry running like a well-oiled machine.
The hero of our story really is ISO 841. This standard is the foundation for absolutely everything we're about to talk about. It makes sure that the G-code written by a programmer in Germany is going to be perfectly understood by a machine tool in Japan. It's what gives us that one, single, unambiguous language for movement.
All right, let's get into this, because this next part, well, it's the key that unlocks everything. You don't need to memorize complex diagrams or dig through manuals right away. Nope, you just need your own hand.
Now, the really cool thing about this is how unbelievably simple it is. Seriously, this one physical gesture is the most important takeaway for understanding the coordinate system of pretty much any CNC machine you will ever come across. So go on, get your right hand ready. First up, your thumb. Point it straight up. That is your Z-axis. Now here's the trick. The Z-axis is always aligned with the machine's main spindle. That's the part that does all the work, all the spinning. So if you can find the spindle, you've found your Z-axis. Simple as that. Okay, next, your index finger. Point it straight out so it's making a 90-degree angle with your thumb. That's your X-axis. A good way to think about the X-axis is like it's the machine's longest runway. It's usually the main direction of travel, typically left to right. And finally, stick your middle finger out, so it's at 90 degrees from both your thumb and your index finger. That right there is your Y-axis, and it completes the whole system. And just like that, with one simple move, you've defined the entire three-dimensional space that the machine operates in.
All right, now that we've got the theory down, let's actually put it into practice. We're going to take our trusty right-hand rule and see how it works on the two workhorses you'll find in just about any machine shop. Let's kick things off with a CNC lathe. So on a lathe, right, the workpiece itself is what's spinning. The main spindle is horizontal, so that means our Z-axis runs horizontally, parallel to the part. The X-axis then moves in and out, which controls the diameter of the cut. It's simple, it's effective, and you only need two axes to do it. Now let's talk about the classic three-axis mill. On these machines, the spindle holding the tool is almost always vertical. So using our rule, the Z-axis is the up and down motion, and that just leaves X as the table's left and right movement, and Y as the front to back movement. And this right here perfectly shows the single most common point of confusion for beginners. Just look at the Z-axis. On a lathe, it's horizontal. On a mill, it's vertical. The key thing to remember is this. It's not about up or across. It's always about the orientation of the main spindle. Once you really get that, you are halfway there. So we've nailed down our linear movements with X, Y, and Z. But a three-axis mill can only come at the part from directly above. So what happens if you need to machine an undercut or some complex curving surface? Well, for that, we need to add rotation and tilt. And this is exactly why we level up to 5-axis control. The naming here is just beautifully logical. The rotational axes are A, B, and C, and guess what? They correspond directly to the linear axes they rotate around. So A rotates around X, B rotates around Y, and C rotates around Z. It's as simple as ABC. Okay, let's actually visualize this. We're going to start with our good old three-axis mill. We've got our X, Y, and Z axes, giving us complete linear control over where the tool is. But again, that tool can only approach the part from directly overhead, which can be pretty limiting. Now, let's add an A-axis. Remember, A rotates around the X-axis. This lets the entire spindle tilt forward and backward,
All of a sudden, our tool can approach the workpiece from all sorts of angles, opening up a whole new universe of machining possibilities.
And for the grand finale, we'll add a C-axis, which rotates the table that the part is sitting on. When you combine the linear movements of X, Y, and Z with the tool tilting from the A-axis and the part rotation from the C-axis, boom, you've got full 5-axis control. This is exactly how you machine those incredibly complex parts like aerospace turbine blades all in one go. Now, 5-axis is pretty complex, I get it, but what about machines with 8, 10, or even 12 axes? It might sound completely impossible, but the amazing thing is, the same basic rules we've just learned still apply. They just get layered on top of each other.
So how in the world do you even get 12 axes? Well, think of it like this. These super complex machines are really just 2 or more simpler machines that have been bolted together. You might have a machine with a second spindle that works on the back of the part while the first one works on the front, or maybe a second set of tools doing another operation at the same time. To control all these extra parts, we just add a set of secondary axes, U, V, and W. They're simply parallel to X, Y, and Z. It's a really logical, scalable system that's all designed for maximum efficiency.
Okay, I know that was a lot of information, so let's boil it all down into a simple, step-by-step process you can use anytime you walk up to a new CNC machine. This is your cheat sheet. Here it is, just a 4-step process. Number 1, always find the main spindle first. That defines your Z-axis. Number 2, use your right hand to instantly figure out X and Y. Number 3, look for any tilting or rotating parts to identify A, B, or C. And finally, number 4, on those really complex machines, check for any secondary slides or spindles, and those are going to be your U, V, or W.
And here is probably the most important piece of practical advice I can give you. While ISO 841 gives us this incredible universal framework, sometimes manufacturers will use different labels for specialized functions. The manual, that is the ultimate source of truth for the specific machine you're standing in front of. Always, always check it.
So there you have it. You now have the fundamental knowledge to walk up to almost any CNC machine on the entire planet and actually understand its language of movement. That barrier between your idea and a real physical object, it just got a little bit smaller. So the only question left is, what are you going to create?